again to the One World Combinatorics Onwards seminar. Our speaker today is Ingrid Vukusic from the University of York, and she's going to be speaking to us about balanced rectangles over Sturmian words.
Thank you very much. Thanks for having me. I hope this will be quite a relaxed 45 minutes. We will be just looking at these rectangles filled with zeros and ones and find out whether they're balanced or not. And maybe before I start, so this example that you can hopefully see here on the first slide, it's generated by the Fibonacci word. And this is what Jeff and I looked at first. I've also given a talk online about this in case anybody has seen it. It was in Lumini in November, so I will be repeating a lot of the things I said there. But since then, I've hopefully completely generalized the main results to any Sturmian words with any irrational rotation angle, and I'll be telling you about that as well. In particular, we'll have to translate the problem from rectangles into intervals and distribution of n alpha mod 1 and a little bit of Diophantine approximation. But even if you don't know any Diophantine approximation, I think this talk should be really accessible for everybody. So let's start. I can't see anybody, but I hope you're all there and feel free to interrupt anytime. Okay. Good. So let's start with the Fibonacci numbers. We all know the Fibonacci numbers. And also in this audience, probably everybody knows the Fibonacci word, but as a warm-up, let's define it together. The Fibonacci word is a sequence of zeros and ones. And so I suggest we just start with a 0, because why not? And then actually, it should be zeros and ones. So let's start with 0, 1. And then let's do the most Fibonacci thing we can think of, which is to just take the previously constructed block and append the one from before, like this. So we got a new factor, we're going to take this one, and we're going to append the one from before, 0, 1, and one more time, 0, 1, 0, 0, 1, and we append the one from the block before, 0, 1, 0, and then after that, of course, we would append this one, 0, 1, 0, 0, 1, and so on. And of course, this generates an infinite sequence, an infinite word. It's called the Fibonacci word. It's very famous and it's got a lot of interesting properties. And one of these properties is that it's balanced. And what does that mean? For example, if we look at the factors of length 5, like this one here, 1, 2, 3, 4, 5, we can determine the weight. How many ones does it have? It's got 2 ones in it. But if we look at a different factor of 5, of length 5, 1, 2, 3, 4, 5, this one's also got weight 2. Now, do maybe all the factors of length 5 have the same weight? Well, no. For example, here we've got just weight 1. But if you look at all the factors of length 5, you will see that all of them have either weight 1 or weight 2. And this fact that they have exactly 2 possible values, that's when we say the factors of length 5 are balanced. And if for every length, all the factors of that length are balanced, then we say that the word is balanced. And it turns out that the Fibonacci word is indeed balanced. Okay, but today we want to look at rectangles, and what we see here is just the Fibonacci word in the top row. And then every time we go 1 down, we shift the word to the left by 1, which is how we get these diagonals with same values. And now we could ask, well, how about the, 2 by 3 rectangles? Okay, are they balanced? Well, this one has got weight 2. Let's look for other rectangles, 2 by 3 rectangles. This one's also got weight 2. Can we find a different weight? Yes, here actually we've got weight 3. But if you look at any other rectangle 2 by 3, you will see that they always have either weight 2 or weight 3. It's really, you can even check it by hand, it's not hard. And so the 2 by 3 rectangles turn out to be balanced. Now, are maybe all the rectangles balanced? Let's have a look at, for example, 2 by 4. This one's got weight 3. Here we've also got weight 3. Let's find a different weight. Weight 2. Okay, this could still be balanced, but no. Here we've got weight 4. So we've got at least three different values, 2, 3, and 4. So the 2 by 4 rectangles are definitely not balanced in our definition. Okay, and so one could ask, well, maybe are the 2 by 3 rectangles the only balanced rectangles, or do we have more of them? Or maybe in other words, for which mn do we have that the m by n rectangles are balanced? And by results, so in 2002, there was a paper by Berthe and Tiedemann. I think they were maybe the first to generalize this balancedness notion to multidimensional word, and they proved, sorry, they proved that essentially you never have all the rectangles balanced, except if you're in a few periodic cases. But in a recent paper, Anselmo, Gemaresi, Madonia, and Selmy found, so this was 2025, Anselmi et al. They found a whole family of balanced m by n pairs, let's say. Namely, they showed that if n is your larger number, and if n happens to be a Fibonacci number, then you will definitely be in the balanced situation. And this matches our examples. So 3 here was a Fibonacci number, and indeed we were balanced. 4 was not a Fibonacci number, but well, I mean, their result is not an equivalence, but still, this is an example where we're not balanced. And what Jeff and I did, we tried to fully exactly characterize all the m's and n's where you are in the balanced situation, and we did it. It was just, we needed one trick that I'm not going to go into detail in this talk, but we needed one trick to translate the problem into something that Walnut can deal with. So Walnut is a software based on automata theory and automata, and it does all the work for you. And then, so you need this one trick, then you type in literally 5 lines of code, you hit evaluate, you wait a couple of seconds, and then you get the answer, which is this automaton, where you can literally read off a bit which pairs m and n are balanced and which ones are not. The only thing you need to know, except for automata, for this to read this, is you need to know that every number can be represented, or every integer can be, positive integer can be represented in Fibonacci representation. What is that? Well, for example, 19, we could just do the greedy thing and see which Fibonacci number fits in here. It's 13, and then we still need 6 more, so we would take 5 and then 1. And so F7 plus F5 plus F2, this would be called the Fibonacci representation of 19. You never need these guys. And if you do the greedy thing, then this representation is unique. As I said, it's called the Fibonacci representation or the Zeckendorf representation. Or for people who know Ostrovsky representation, this is, of course, just a special case of Ostrovsky representation for the golden ratio. Okay, so, and then if you know this, you can translate this into a string of zeros and ones. You can go back to the automaton, you can stare at it really hard, and you can see that you can find out exactly which pairs m and n are accepted by this automaton, and those are the ones where we are in the balanced situation, and it turns out that they are exactly the numbers of the following 3 shapes. So I'm assuming that we've got 2 less or equal to m, less or equal to n, and then essentially we've actually got 2 cases. The first block of cases is where we've got the split between the digits, so m only contains small Fibonacci numbers and n only contains large Fibonacci numbers. Then we've got this edge case here, where somehow we'll see why this is important later, why all of this makes sense, we'll see later, but you have this parity restriction in the representation of n. And then the other special case where we are balanced is where m is a Fibonacci number, and again, we've got some subtle condition. Okay, so this is the answer. You get it essentially for free from Walnut, but in this talk, we want to understand why are these the answers and what's going on. And to understand this, we need to translate, well, we're going to use a different definition of the Fibonacci word, because the one I showed you was, in my opinion, the most fun one, but it's not the most useful one in this situation, because The one that we're going to use, so there are many, many different definitions of the Fibonacci word, but the one that we're going to use is via irrational rotations. So I've drawn here the unit interval in a circle. We start here, that's 0, and then you go this way, 0.1, 0.2, 0.5, and so on, and then you're at 1, but 1 goes back to 0. So this is the unit interval, and we always rotate by this phi prime. It's essentially 2 minus the golden ratio. Just think of it as something to do with the golden ratio, a fixed irrational angle, and we can rotate by this and sort of hop around on this unit circle. And we've got this red area, which is just before the integer point, and it's got the same length as the rotations that we're doing, just this way. And then every time we land in the red area, like here, we're at the fifth point, we land in the red area, and we record a 1. After that, we land in the white area and we record a 0. Then we have 1, 0, 0, 1, 0, and so on. And if you compare this sequence here to the one that we together constructed at the beginning, you can check that it's the same sequence, at least at the beginning. And now I'm also going to give you some intuition for why these are really the same sequence, because this will also be relevant later. And to understand this, in case you've not seen this before, you can explain this via the basic properties of the golden ratio and Fibonacci numbers, or like the basic, what connects the golden ratio and the Fibonacci numbers is, I think this is a very generally known fact that the golden ratio is roughly the ratio between consecutive Fibonacci numbers. And if the Fibonacci numbers get very large, then this is an extremely good approximation. And in other words, this means that if we multiply the golden ratio by fk, we get roughly fk plus 1. And more generally, we get very close to an integer. So phi times fk is very close to an integer. And now let's see if this, what I'm claiming, if we can see this on our little animation. So Fibonacci numbers, 3, for example, is a Fibonacci number, and the point 3, phi prime, is indeed pretty, well, it's sort of close to the integer point. The next Fibonacci number is going to be 5, and indeed 5 is even closer to the integer point. And then we go on, and 8 is even closer, and we can say that we alternate from which side we're approximating. And in fact, every time we get a Fibonacci number, we get closer to the integer than we've ever been before. This is called the best approximation property, best approximation. And for anybody who knows continued fractions, this is of course just the property of continued fractions, because the Fibonacci numbers are exactly the denominators of the convergence to the golden ratio. Okay, so this best approximation property will be important later, but also it explains sort of why our two definitions of the word are the same. Because, so look here, for example, at the Fibonacci number 13, we get very, very close to 0. So after that, what we see is sort of like when we started at the very beginning, because we started at 0, and then every time we get back close to 0, everything that happens later for a while looks almost the same way as at the very beginning. And this is exactly how we constructed the Fibonacci word at the very beginning. We said we constructed these blocks where the first one had length 1, the second one had length 2, and then we concatenated them, and we got length 3, length 5, length 8, and so on. Of course, we get Fibonacci lengths. And what happens after one block ends? Well, here we append the one from before, so we start all over again. And I hope this sort of, sorry, roughly justifies why these two definitions might be the same. And this definition here with the rational rotations is the one that we're going to use because it's more handy, and also because it directly generalizes to Sturmian words where you just change the angle to something else and not the golden ratio or minus the golden ratio. Okay. So let me write down this new definition. One way you could write it down is, okay, if A1, A2, A3 is the Fibonacci word, then AN now is 1, if and only if we are in the red area. And what does that mean? Well, the fractional part of n alpha is in the red area, and that's just the interval 1 minus phi prime to 1. Okay, and one more way to write this down, or is simply an equals the floor of n plus 1 phi prime minus floor of n phi prime, because either these two floors are the same, then we get 0, or actually as we go from n to n plus 1, we hop over the integer point and we get 1. And this is exactly what we want, because being in the red area means that after that, we're going to hop over the integer point. That's exactly the definition. Okay, and now this is handy because this we can just use to compute things directly. For example, we could start by checking the balancedness property in the one-dimensional case. So remember, balanced means that all the blocks of a fixed length, say of length n, have roughly the same weight. So let's look at the blocks of length n minus 1. Then we've got I plus 1. And counting ones in this block is the same as just adding up all the digits. So we want to find out what the value of this is. And now I'm going to use the definition I wrote down previously, and we get for the first term just I plus 1 phi prime minus I phi prime. And then for the second one, this is the only boring computation we're doing, I plus 2 phi prime minus I plus 1 phi prime, and okay, and so on. And then at the end, we get floor of I plus n minus 1 plus 1 phi prime minus I plus n minus 1 phi prime. And now everything telescopes away, like this cancels it out. This is going to cancel out with something. This is going to cancel out with something. And the only terms that are left are the smallest one and the largest one. And we get floor of I plus n phi prime minus I phi prime. And if we ignore the floors, then of course this would be just n phi prime. And if you check the details, then you will see that this is the floor of n phi prime, but you could also be one bigger. You could have plus 1 if. So when do we have plus 1? Well, if in this term here, actually, you sort of jump over the integer point. So if the fractional part of I phi prime plus the fractional part of n phi prime, if this exceeds or is equal to 1, then you actually have to add plus 1. You can check the details. It's just about the fractional parts. And so what we see is that every block of length n has either weight, this fixed weight n phi prime, or maybe the same but plus 1. And this is fine. We said that balance means 2 values. Okay, and now we can use this formula directly to compute the weight for the rectangles. So remember, we wanted to sum over the rectangles where, let's say we've got index I in the top left, and let's say we've got n columns, and let's say we've got m rows, I plus m minus 1, and then this guy is going to be I plus m plus n minus 1. Okay, and now we can just reuse what we already know. We know how to sum over the rows, for example. So let's sum over all the rows. Check a different color.
Oh, so sorry for interrupting you.
Yes.
But m plus n minus 2?
Yes, thank you very much. Yes. Thank you.
Thank you.
Great. So now we're going to sum. I'm glad somebody's listening. Very, very reassuring. So now we're going to sum over the rows. At first we have I plus 0, and in the end we're going to have I plus m minus 1. And so for each row, we take the formula from before. Here we've got length n, so we can just use the same formula. We've got n phi prime, floor of n phi prime. And then we need to add these conditional terms, which I'm going to rewrite as, well, we're checking whether this guy is large, whether it's in the interval 1 minus n phi prime and 1. So I'm going to write this as, well, check whether I phi prime is in the interval 1 minus n phi prime 1. So these are just the fractional parts, but everything is mod 1 as well. So don't worry. The only thing is here we had I, and then later we have I plus L. So I need a plus L here. And this is essentially the exact formula for the rectangles. Let's just simplify it one more time. We can see that this term here does not depend on L, so we can pull it out, and we get just m times floor of n phi prime. And then we get this sum, and we count points in certain intervals. And I'm just going to rewrite one thing, which is here we've got the point sort of that we're looking at is shifted to the right by I phi prime, but instead we can also shift the interval here to the left by I phi prime. So I'm going to write this as, here's the interval, 1 minus n phi prime minus I phi prime, 1 minus I phi prime. Oops. And the point is now just L phi prime. Okay, so what are we counting here exactly? We are counting points out of sort of m points from 0 to m minus 1. We're looking at the points and we're checking whether they are in this interval. And this interval has length exactly n phi prime. So the length is determined by our n. And these i's, these I phi's just cause a shift. But we're interested in all the i's, right? We're interested in all the rectangles. So we also sort of need to consider all the shifts. And if you know that I phi prime is uniformly distributed mod 1, then of course, essentially we need to look at all the intervals. And we can do this in GeoGebra. I've got another one here. So I said we've got m points, like let's say 9 points. We go from 0 to 8 just because it's easier. And then we've got the interval length. Sorry, let me just switch between those two. We said the interval length is governed by n phi prime. So if, for example, n equals 19, then we get this interval length. And then if we want to know if our rectangles are balanced, we need to know if these sums, if these counts of points are always the same up to 1. And here, for example, we have 2 points in our interval, and then 3 points, and then 2 points, and then 3 points. So if it keeps going like this, always 2 or 3 points, then we know that, of course, our rectangles are also balanced. But if our count gets out of balance, then we're not balanced. And indeed, if you look here a little bit further, suddenly we get just 1 point, while on this side, we can even get 4 points. So this would be an example where we are not balanced. Okay, so we've translated our problem from rectangles to intervals. I'm gonna call these like balanced intervals. And now we want to find out, well, for which mn are we balanced? And to do that, we need to speak a little bit more about Fibonacci representation. I already showed you how to represent 19 in Fibonacci representation, but now I want to tell you why this is so amazing. The thing is that if you asked me, Ingrid, 30 phi prime, where is this in the unit interval? Like, where is this mod 1? What's the fractional part of this? Okay, so remember phi prime was 2 minus the golden ratio. This is roughly 0.38. And I would be like, well, I don't know. We can do the maths and work it out. I don't know. Okay. But if instead you told me 30 actually in Fibonacci representation is 21 plus 8 plus 1, then I'd be like, oh, hold on. I know what to do. 30 phi prime, I can just write this as 21 plus 8. So that's F8 plus F6, those are these two numbers, phi prime, plus 1 more phi prime. And now I know where this number lies because I know by the best approximation property. Remember, if we multiply phi prime by a Fibonacci number, it's going to be super close to an integer. So this is going to be roughly 0 or maybe 1, depending on how you look at it, mod 1. And so I can immediately, just by looking at 30 in Fibonacci representation, I can say, this is roughly going to be where phi prime is. I mean, I could work out the details just from knowing how large the large digits are, but it's going to be in some interval around phi prime. And yeah, so I hope you can see why this Fibonacci representation is so nice. And just as a little anecdote, I was giving a talk recently, and afterwards somebody made fun of me because I was so enthusiastic about the Fibonacci representation, because they were like, oh, Ingrid, so if somebody gives you 0.257 and then tells you, and you've got some extra digits in decimal representation, are you then also going to be excited that this number is somewhere in the interval 0.257, 0.258? Because it's the same thing. It's literally the same thing. This Fibonacci representation fits with the golden ratio. And by knowing the small digits, you know which interval your point is going to be in. And for anybody who knows Ostrovsky representations, this also works in a completely general setting. So what we did here was the Fibonacci numbers are the convergence to the golden ratio. But if you take a different alpha, so let me just very briefly do this. I'm not going to introduce them rigorously, but if you have any irrational alpha, then you can compute the continued fraction expansion, and from this, instead of the Fibonacci numbers, you get some other best approximations that get you super close to integers. And then, if you have a number n, and you want to know where n times alpha lies, mod 1, then you just need to represent n as a sum of these q's, and you can just exactly as before, you can do the greedy thing. You can do the greedy thing, and then you get a representation as sum from, say, k to n, some coefficients, vk, qk. And in this general setting, if you do the greedy thing, you will see that you actually might need some larger coefficients here. And I'm not writing down the details, but if you do the greedy thing, you get the Ostrovsky representation. It's called the Ostrovsky representation, and it has all the nice properties that you also get for the Fibonacci numbers. Okay, so this is obviously somehow going to help because it exactly describes where our points lie, mod 1, and we said that somehow these points are important. So now let's look at the proof strategy, or like the solution strategy for how to characterize the M and N to find balanced intervals or balanced rectangles. It's the same thing. Okay, so the way I thought about this is actually the same trick that Jeff and I used for the Fibonacci word with walnut. The trick is not to try and count all the points, but instead to see how the count changes as we either go through the rectangles or as we go through the intervals. And here we can just go through the intervals. It's what I showed you before. I slid this across the unit interval. Here we had 3 points, 2 points, and everything that keeps happening is here we gain this point, and then next we lose this point here. And then we gain a point and we lose a point. And as long as this keeps going on, gain, lose, gain, lose, gain, lose, we are of course balanced. But if suddenly, so here we gain, but then we lose this point, and then we lose another point. As soon as we lose 2 points consecutively, we know we are out of balance. So we need to somehow capture this idea. And the way I did this is I just defined a function that maps points to other points. Let's have a look. So we have m points, and we've got interval length n phi prime, just like before. And now what I'm saying is, fix some point like this one here. And let's say, so this is 11 phi prime. Let's say 11 is our L. It's going to be called L, the coefficient. And then what I'm saying is look at the end point of your interval. This is going to be L plus n phi prime. And this point, of course, is not in our collection of points. The collection of points is 0, 1 phi prime, m minus 1 phi prime. It's not in here because L plus n is larger. We said that n is the larger number. So what I want you to do is find the next closest point in moving direction. And this point is sort of the map of this point, or actually the way I defined it is that the number 4 is the map of 11, or f of L. So I defined this function f that maps 0, 1, m minus 1 to itself in this way that I just described. And the reason I'm doing this is because I'm claiming that f is bijective if and only if our intervals are balanced. Maybe this is obvious, I'm not sure. I'll just briefly show it in this animation again. So the point is that, for example, if we focus, okay, this is a different angle, but from here, this point, we know we just lost it, and then the function is going to tell us what's going to be the next point that we're going to gain. And as long as this keeps alternating, so as long as every point maps me uniquely to another point, it sends me uniquely to another point, I know I'm going to be alternating between gaining, losing, gaining, losing, but as soon as, for example, here, both of these points, this point has this point as an image, and the next point also has this point as the image, we're not injective, and that's why we suddenly lose 2 points without gaining. Okay, I hope this is plausible. So we've translated our problem. Let's remember we had the rectangles, we translated the problem into intervals, and now we've translated this problem into a certain function being bijective. Okay, and then we need to do one more step because this function is not very handy to work with, but the way that I think about this function f is I think, how do I get from this L plus n phi prime, how do I get to an integer, in this case 4, that is in the range, right? L plus n was not in the range. We need to get back into the range. We need to subtract something. Let's going to call this number, we subtract minus x of L. And then we get back into the range 0 to m minus 1. So we need to get back into the range, and this subtraction needs to cause the minimal shift in rotating direction. So we don't want to go this way, we want to go that way, and also we don't want to end up at this point here, we want to end up at the closest possible point out of the collection of points that we have. And that's where Ostrovsky representations come into play, because we know, well, the integer x of L has to be in some range. I'm not going to write down the details, but the range depends on, well, on L plus n and on the range. So it depends on n, on m, on n, and on L. It's some range of integers that we can pick from. But within this range, we need to pick the one that causes the minimal shift to the right. And by Ostrovsky representations, we know it has to be some number that only has large digits. And the parity of the smallest digit will determine the direction in which we go, and we want to go in one specific direction. And so I'm sparing you the technical details here because it is quite technical, but you can just examine this function xl, and you can find out that you will see that in certain ranges, this function has certain fixed values. And then this helps you because, remember, how did we get this? We said f of L should be L plus n minus this xl. That's how we defined it. And so if we want to know whether f is bijective, n is fixed, we can instead check whether xl minus L is bijective. And this is something you can then, by working out the details, you can exactly figure out when you are bijective and when you're not bijective, and that solves the problem. Okay, so I know I've dropped the technical details, but this is really the idea. And maybe as a warning, if you go and read the paper, and actually I also defined 2 Fs. I defined an F left and an F right, because sometimes I want to focus on one direction and sometimes I want to focus on the other direction. It's because there are so many cases in the proof that I wanted to make this technical part, which is looking at these ranges and looking at Ostrovsky representation properties, I wanted to make this part as short as possible. So I did a lot of tricks around it to be able to assume a lot of things for the technical part. But yeah, so I worked out all the details, I hope, and this is the current main theorem. It's not as bad as it looks. It has just 4 cases, and the first 2 cases are really easy to understand. They are the same as we had for the in the Fibonacci case. Remember, the first 2 cases were split cases, so where m only has small digits up to some capital N, and n only has large digits. So, and also remember, this was the very, no, I didn't even show you this. I'm sorry. Why is this obvious? Actually, this is obvious because if n only has large digits, like for example, 21 is just a large Fibonacci number, then of course your interval is going to be very, very small. And so all the intervals are going to have exactly 0 or 1 points. Yeah, and this is also the second case in the split case. M only has small digits, and then in the edge case, n does contain the same digit, but then the parity restriction here guarantees that your interval is going to be smaller than the smallest gap that you see, and therefore, of course, you are balanced. Okay, so it's not actually hard to prove that in these cases you are balanced. The problem is to prove that you're not balanced in all the other cases. But there are 2 more cases where you are balanced, which is if m happens to be a convergent, that's the equivalent of just being a Fibonacci number. And then we've got some technical parity restrictions in the large digits of n. And then there's another case which does not show up in Fibonacci numbers because with Fibonacci numbers, semi-convergence do not really exist. But in general, you can have things called semi-convergence that have this shape, and then n again has to have some parity restriction in its large digits. And these are exactly the cases where you are balanced. As I said, the green cases are where your interval is extremely small. The blue cases are a bit harder to explain. Roughly speaking, M being a convergence guarantees that your points are particularly evenly spread out and things work out. Okay, so yeah, I mean, I have this little example here to see that really this result works also for not the golden ratio. So for example, I picked here alpha to be pi over 4. For people who know continuate fractions, this is the continuate fraction expansion. And then from this, you can compute the convergence. So this is now, instead of Fibonacci numbers, these are the convergence. And then if we want to know whether, for example, the 2 by 10 rectangles are balanced, we don't have to look at the infinite Hankel matrix. We can just represent 2 and 10. So m is 2, n is 10 in this greedy way with these q's. So 10, for example, would just be 9 plus 1. That's q4 plus q1. This one we actually, this one we actually don't need. And for 2, so here you see that in the general setting, you do need coefficients. We would just have to write this as 2 times q1. And now we need to check if we are in one of the special cases. Well, none of them is a convergent, but we are in the split situation where q1 is the largest one showing up here, and it's also the smallest one showing up here. And the parity restrict condition 4 has a different parity from 1 is satisfied. Yeah, this is the condition here. And so we are in case 2, and the theorem tells us that we are balanced in this case. I can do just one more example. If we picked m, for example, 5 instead, 5 we would represent as q2 plus q1. And then you can really see we are in none of these 4 cases, and we immediately know that we are not balanced. Okay, so I think that's already all I wanted to say.
Wouldn't
Yes.
it just be Q3, actually, in your example?
Oh, I probably messed up. Yes, I'm so sorry. Okay, I made a mistake when I typed up the Q's. No, I didn't. Yes, but good point. So this would be Q4. And then this would again be this. Oh, so then we are balanced again. Okay, I need to check where I made the mistake.
Q3, Q3.
Q3, excellent. Okay, good. Thank you. So, okay, I picked an even more obvious thing. No, sorry. Okay, so this is sorry, I'm sorry. Okay, so now M is Q3, which is in between Q1 and Q4. And now, now we would have to check again. So this is, this is the case where M is a convergent, right? M is Q3, okay? M is a convergent. So now we need to check whether the larger digit in N, whether it has the same parity as the M. And right, but Q3 and 4 have distinct parities. Okay, I did, and there was a reason behind this example. 3 and 4 have different parities, and so we are in none of the balanced cases in the theorem, and therefore we know that we are not balanced. Okay, thank you very much. And that's now all I wanted to say. Thank you very much.
Great. Thank you very much, Ingrid, for a nice talk. Does anyone have any questions? Hajime.
So thank you for nice talk. So in previous work of in previous year work with Professor Jeffrey Charlotte, you've also considered a two-more sequence. Is it right?
Yes, I think so, but I don't really remember much. But yes, we did remember. We did consider a few other sequences as well. I think probably Jeff remembers better.
Yes,
yeah.
we did. Yes.
Yeah. So it's balanced at the most four. Is it possible to generalize so in this direction? So you generalize to Fibonacci to Sturmian verse.
I'm not sure. Well, so, 2A Morse is pretty easy just because if you want to count the number of ones in any interval, it's, from the ith to the jth, that's very easy. So, we could do the same thing for Fibonacci in principle and any sequence where it's easy to do that, but most automatic sequences won't have that property that it's easy to count how many letters occur in an interval, and I don't know how to do it in that case.
Okay. Thank you.
Are there any other questions?
I just wanted to thank Ingrid because we worked on this together, and I was content to just say, hey, look, here's the result by Walnut. But Ingrid was not content, and so she dug much deeper. And now she can explain to me why the original theorem is correct, which I really appreciate. Thank you, Ingrid.
Thank you for the problem.
So I had one question. In the for the shapes that are not balanced, I guess the imbalance can be arbitrarily large. Is that true?
Yes. So there are. I forgot to mention a couple of things. I'm sorry. So it can be roughly log n of, and this is sort of known because I didn't say this. I forgot. I had on one of the slides I had the word discrepancy. So the way that people from Diophantine approximation and dynamical systems and things think about this is that in general, if you have like points that are distributed mod 1, and then you can take any interval and you can sort of say what is the expected number in this interval of points, and then how much are we off from the expected number. That's called the discrepancy. And there exists bounds for the discrepancy of the distribution of n alpha mod 1, and these log n is, I think, a lower bound. So it's already known that you can get arbitrarily large discrepancy, and this discrepancy is also going to show up in our intervals.
Thank you. Are there any other questions? Okay. If not, thanks again, Ingrid.